This is the quadratic formula, and this is a donut, or at least a sketch of its surface. Today I want to tell you a bit of a story about how we can use this thing on the left to study this thing on the right. And the story starts with this curve over here, and well, it's curvature. I think you might agree with me that this part over here has more curvature than this flatter part up here. Now, turning this intuition into something a bit more tangible has historically been a bit of a tricky problem. So instead of looking at a general curve, let's just look at these two circles over here. And I hope you'd also agree with me that this smaller circle here has more curvature than this bigger circle. So what we're saying is that the curvature of circles should be inversely proportional to their size. And this observation is how we're going to define the curvature. So say this circle has radius capital R here, then the curvature, which I'll denote with the Greek letter kappa, we're just going to define as 1 over R, 1 over its radius, right? So exactly inversely proportional to its size. And to generalize this to curves, what we want to do is to compare our curves to circles. Say I want to find curvature at this point. Well, I can slide the curve against the circle here, and we see immediately that our curve bends too much, right? I can try to fit the curve to this circle here, but I'll have to bend the curve. I'll have to change its curvature. If we look at this smaller circle that we had before, well, it looks like it's a much better fit. So what we want to do here is to define curvature as the curvature of this circle of best fit. Notice that this circle of best fit is tangent to our curve at this point P. So here's the tangent line, and let's look at all of these other tangent circles, right? These circles that sit on top of this tangent line. And of course, some of these circles are much better fits than others. So what we want to do is to say, well, if we start with any one of these circles, well, how can we get to the circle of best fit? And the idea is to start by picking another point Q on our curve. Then Q uniquely defines one of these tangent circles, so let's see what happens to these circles as we move Q around. What we see is that as Q limits to P, this circle limits to this circle of best fit. And so that gives us a way to define the circle of best fit. It's just this limiting circle. And we call this circle of best fit the osculating circle. By the way, this process might feel a bit familiar to you, in that it's pretty much the same construction that we use to define tangent lines. And to find the tangent line, we had a derivative. So let's see if we can say something similar about finding this osculating circle. Say I want to find the osculating circle at this particular point. The first thing I want to do is to simplify the problem a bit. Notice how I can move this curve around without changing its curvature. So why don't we move this point to the origin? That means that x and y are both equal to 0. But I can also rotate this curve around, so I can make sure that I'm moving this point to the origin so that the tangent line to this curve is the x-axis. Now, in general, this curve is not going to be a function. See, it doesn't pass the vertical line test. But we can zoom in on just this small portion to get something that is the graph of a function. So here's a picture. Let's see where those assumptions take us. The curve being a graph means it's defined by an equation y equals f of x. And because this graph crosses the origin and has a horizontal tangent line there, we know that f of 0 is equal to 0, and also that f prime of 0, the first derivative, is equal to 0 there. Now this point Q here, since it lies on the curve defined by y equals f of x, then it has coordinates x comma f of x. And this circle here, let's say it has radius capital R, will have center 0 comma R, and that means we can define it using this equation here. X squared plus y minus r squared is equal to r squared. So now we have the equation of a circle and also a point contained on that circle. And we can use this to solve for r as a function of x. And to do that, I'll substitute f of x into y. So the equation of the circle turns into something like this. And a bit of algebra shows that r is equal to x squared plus f of x squared, all divided by 2 times f of x. At this point, I also realized that I forgot some absolute value bars, in particular around this f of x in the denominator. But let's see if we can compute the radius of the osculating circle. That's the limit of r as x goes to 0. I'm going to fast forward through these computations, but they sum up to applying L'Hopital's rule twice and then evaluating f and f prime at 0. And what we end up getting is that basically everything cancels out except f double prime, the second derivative. Note that I'm again missing some absolute values, but in the end we find that the radius of the osculating circle is 1 over the second derivative, and so the curvature, its reciprocal, is just the second derivative, or at least its absolute value. Now we just computed curvature at the origin assuming we had a horizontal tangent line. But moving the curve around won't change the second derivative, at least as long as I don't rotate the curve. So we actually have a slightly stronger statement that as long as we're looking at a point on the curve with a horizontal tangent line, then we can compute curvature at this point just by computing its second derivative. And to use this to study surfaces, we're going to start by making the same sort of simplifications we used before. Namely, it is the graph of a function, so defined by this equation z equals f of xy. And we're also going to be looking at curvature only for points with a horizontal tangent plane. Next, I'm going to pick a direction in this tangent plane. So this direction is a vector, and let me call this vector u. And I'm also going to pick this vector to be a unit vector. That is, it's a vector with length equal to 1. And so instead of looking at the whole surface, why don't we look at the surface but only in the direction of u? That way we get a curve, and this curve is called a normal section. So let's study the curvature in the direction of u, that is, the curvature of this normal section. And for this discussion, we're actually going to add signs to curvature. So upward facing is positive curvature and downward facing is negative curvature. One of the consequences of this is that the curvature of this normal section is just the second derivative without absolute values. Let's give u some coordinates, u1 and u2. Then differentiating in the direction of u is something called a directional derivative, which I'll denote d sub u. So to compute a second derivative, all we need to do is to compute 2 successive directional derivatives. And since we picked u to be a unit vector, then the directional derivative is just the dot product of u with the gradient of f. And I'm fast forwarding through these computations because all I'm doing here is just applying the definition of the directional derivative twice. This end result that we have here, however, is a bit more special. And that might be a bit more clear if I label u1 as x and u2 as y. Because what we have here now is this quadratic polynomial in 2 variables whose coefficients are the second order partials of f. So let me label this as q sub f. You might see that q sub f is looking remarkably similar to the types of quadratic polynomials that the quadratic formula applies to. And what I mean is that if I relabel the coefficients of q sub f by a, b, and c, then after setting y equal to 1, we get this quadratic polynomial in a single variable, which is exactly what the quadratic formula applies to. And in fact, we do get this sort of a new quadratic formula that applies to our quadratic polynomial in 2 variables. It's actually pretty much the same as our usual quadratic formula, but with some extra y's tossed in there. And instead of the solution being a number, now the solution is this equation. But what does this mean? Well, let me label this term here alpha, then our solutions look like x is equal to alpha y. And this is just a line. If I rewrite this as y equals 1 over alpha times x, we see that it's a line through the origin with slope 1 over alpha. So what's happening here is that q sub f defines a surface, and what you see here is this surface changing as I vary the coefficients of q sub f. But the quadratic formula also involves setting q sub f equal to 0. And what this means is intersecting or restricting our surface to the xy plane. And so here you can see the lines that we got as solutions to this new quadratic formula. But we don't always get two solutions. As I vary the coefficients here, right, we can see some of the solutions disappear. And that's because in the quadratic formula, we have this thing called the discriminant sitting under the square root. And if the discriminant is positive, we get two solutions. We can see the intersection factors into two lines, and our surface looks something like this shadow over here. If our discriminant is equal to 0, we get exactly one solution, so exactly one line, and the surface looks like this stretched out parabola. And now if we have a negative discriminant, then we have no solutions, and this intersection is now just a single point, and our surface looks kind of like a bowl. So we see that it's the quadratic formula that governs the geometry of Q sub f, and when it breaks into these different forms, which we can now use to study curvature, because curvature in the direction of u, this kappa sub u here, is just Q of f evaluated on our unit vector, right, on u1 and u2. Now, being a unit vector here just means that u1 squared plus u2 squared is equal to 1. And so if I relabel u1 and u2 with x and y as I've done before, we just get the equation of a unit circle. So let's see what happens to Q sub f if we restrict it to the unit circle. So here's the graph of Q sub f again. Then this restriction is a curved line on this graph. Picking a direction as we had before now picks out a point on this curve, and the height of this point is the curvature in that direction. So you can see how it varies as I move this direction vector around. The largest and smallest curvatures are called the principal curvatures of our surface. The max is kappa 1 and the min is kappa 2. And it's these principal curvatures that Euler used to study the curvature of surfaces. And one of the things he showed was that these principal curvatures always occur in perpendicular directions. And you can see how that persists even as I change the coefficients of Q sub f. And we can actually see why that's true. It's because this curve here inherits some symmetries from Q sub f. Because Q sub f is a quadratic surface, then we can see these horizontal cross-sections are, well, they're conic sections. These always have a major and minor axes, and the maxes and mins lie on these major and minor axes. And there's this miraculous connection between the principal curvatures and the discriminant of the quadratic formula. Up here, I just have our horizontal tangent plane assumption. Then if we take the product of our principal curvatures, we get minus 1/4 times the discriminant of Q sub f. Since the coefficients of Q sub f are made of the second order partials of f, let me also rewrite this in terms of these second order partial derivatives. And we get this, well, maybe slightly cleaner expression. Now, this product of the principal curvatures is something called the Gaussian curvature, something that we usually denote with this capital K here. It's at this point that I also want to mention this Hessian matrix for f. It's this 2x2 matrix whose coefficients are just the second order partials for f. And what we see is that this Gaussian curvature is the determinant of this Hessian. And it's not a coincidence that there's this relationship between this Hessian and the discriminant of Q sub f. In fact, we can write Q sub f in terms of this Hessian as this product of matrices, where these are 1x2, 2x2, and 2x1 matrices. And there's this amazing theorem by Gauss that says curvature is intrinsic to surfaces. And what I mean is that we can look at this piece of paper, which, well, has zero curvature because it's flat, but I can also bend it around. And while bending this piece of paper changes its principal curvatures, this piece of paper is also rigid in a sense. I can't stretch it out. Gauss tells us that as long as I'm not stretching this piece of paper out, its curvature is going to stay the same. And we actually saw this earlier in this surface here, when Q sub f had a discriminant of 0. And so it has zero Gaussian curvature even though it's not completely flat. And it's actually because of this that any map of the Earth has to somewhat distort areas a bit. But I want to get back to this donut that we started the video with to summarize what we now know. First, this inner rim here, at least locally, looks kind of like a saddle shape, and that means it has negative curvature. On top, we get a bit of a flat spot that looks kind of like we're bending this piece of paper, and so here we get zero curvature. Then as we move out, we get to part of the surface that's a bit bowed out. So the curvature out here is positive. So to summarize, the quadratic formula and curvature tells us a bit about whether we look like this bowl on the bottom left, or the saddle or Pringle shape on the top left. By the way, I did all of my animations in GeoGebra, so if you're interested in playing around with some of the things I showed you today, well, check out some of the links in the description. Anyway, that's all I have for you today, so thank you so much for watching. I hope you learned something, and, well, maybe I'll see you around.